as you notice that we are slowly moving more into more networking issues. Kerberos itself was networking, because before Kerberos we were talking about all this encryption and cryptography which didn't really require networking. You could just do it on a single node. But Kerberos is one thing that we talked about that required an organization and a network and so on and so forth. Now transport layer security is exactly the same thing, is that now on the internet. And many of you have heard about SSL, so we'll talk about that most of the time and then tell how it is related to TLS and HTTPS. And then toward the end we talk briefly about SSH. So if you want to secure applications, you have choices of many layers. You could secure the IP layer, and we will talk about that. That is called IPsec. Or you could secure the TCP layer, and that is what we are going to talk today, and that is called TLS, transport level security. And or you could secure the application, which is done in SMTP by using SMIME. Basically in SMTP, which is the mail protocol, you could encrypt the content and then send over. Alright, so that is called SMIME. So the advantage of doing at IPsec layer is that all protocols, all transport protocols are covered and all applications are covered. Alright. The advantage of doing at TCP again is similar, is that all application protocols are covered. And the advantage of doing in the application is that basically not, this is not an advantage, but basically is that you can design it very specific to a protocol or an application, although it doesn't cover any other application. Alright? So in some sense lower is better. However, there are several problems with IPsec, that you see more application of TLS and SSL in the internet than IPsec. So every time you do HTTPS, you are doing SSL or TLS. And we will use them interchangeably almost, because, as we'll see the next slide, TLS is simply an update of SSL. What they provide is four things. First, they provide the facility to crypto negotiate. Negotiate what encryption scheme we will use, what hash methods we will use, so you can negotiate the one side then the other side. By the way, this is transport, so there are only two sides, so there is no negotiation with the network. It's just end-to-end, receiver and the sender. Key exchange, so then you can exchange your secret key. Once you know what algorithm you are using, then you can use that, and that is done using public key certificates. Then privacy, obviously you do encryption. Once you have the key, you can use encryption. And integrity, once you have the hash, you can ensure that the message is not changed by anybody on the way. So these are the four things that the SSL provides: crypto negotiation, key exchange, and then privacy and integrity. So the history is that SSL was developed by Netscape. As you know, Netscape was the first company to put out a browser back in 1994. When the browsers came out, people said, well, we can't use it because there is no security. So they invented a method. Actually, they just used the technology available at that time. So they invented a method, failed twice. SSL version 1 was so bad when never deployed. Version 2 had major issues. So version 3 developed very quickly. And version 3 is what is being used quite a bit. And then when version 3 became deployed, then IETF took it over and made a standard based upon version 3, and that standard is called TLS. The changes are, so the TLS is actually, when you send messages, TLS is encoded as version 3.1. When somebody negotiates SSL version 3.1, they are negotiating TLS version 1.0. So the differences are small, but the protocol do not interoperate. So you cannot have one side speaking SSL version 3 and the other side is speaking version 3.1, even though they are just 0.1 version apart. So if either both sides speak 3, both sides speak 3.1. Obviously nobody wants to speak version 2 because version 2 is known to be have a problem. So we don't speak version 2. So version 1.1, so after this version 1 was done, TLS version 1 in 1999, version 1.1, which is encoded as SSL version 3.2, was done in 2006. That added a protection against CBC attacks. So there were some CBC attacks that were discovered in the meantime, so that was protected here. And then there is a TLS version 1.2, TLS version 1.2, which is encoded as SSL version 3.3, that was added in 2008. So TLS version 1.2 was done in 2008, and it added many of these things. It replaced MD5 SHA-1 with SHA-256. It replaced MD5 SHA-1 for the hash with SHA-256. It replaced MD5 SHA-1 from the signature, in the signature field, with SHA-1. So MD5 was removed, basically, in summary. And it enhanced the clients and the server's specification for hash and signature algorithms. So some new algorithms were added for hash and signatures. And it added authenticated encryption ciphers. So basically, authenticated encryption means that you have encryption along with message authentication, right? So that was added. And then extensions definition. So basically they allowed some more extensions, and so they just defined a way to define extensions. So people can add extensions, and then they added AES. Anyway, this was 2008, and now after that 2008, so we are almost very close to right now, they have another RFC which did not generate a new version of TLS. It's still called TLS version 1.2, but they added a requirement that you will never use version 2, SSL version 2. Previously there was not a requirement, and some versions accepted it, or some implementations accepted it. Now if you are doing 1.2, you will not accept version 2. Summary of this is that SSL and TLS, they are one basically extension of the other, update of the other, and they are just coded in the same kind of messages. Only the version number for TLS 1.0 is SSL version. What is the version for 1.0? SSL is 3.1, and for 1.1, 3.2, for 1.2 it is 3.3. So they are going up by 0.1 every time they go up 0.1 here, and the messages are still the same. So when looking at a message, the only way you can tell the difference between SSL and TLS is if it is 3 or below, then it is SSL. If it is above 3, then it is TLS. So SSL itself consists of 4 protocols, and they are organized as follows. There is one thing called Handshake protocol, second is the Cipher Spec, third is Alert. All of them run on the record protocol. So we will actually go in this order. Book actually goes in the bottom up, I am going to go top down. So basically we will talk about these protocols. So what the Handshake does is, Handshake negotiates what algorithm we are going to use, period. What is the crypto, what is the hash, and so on and so forth. In fact, you might even get the key with Handshake. With Cipher Spec, change Cipher Spec is very simple protocol. It simply says, okay, all right, let's begin. That's the only command, which says that, okay, so we negotiated the key, now let's begin using that key. So that is one spec. And then Alert protocol tells you any errors that might happen. It's like ICMP for IP. All right, all the error messages are sent using Alert protocol. And Record protocol is what is the basic main protocol which provides the encryption and the authentication. So this uses the keys that were generated using Handshake, and so everybody has all of these messages are encrypted using the Record protocol once the keys are done, right? So. And HTTP is shown here because HTTP would be an application that will use SSL, so it uses like this. Basically, all of these things are done, and SSL Record protocol is ready to go, and then HTTP will send messages. which are encrypted and authentic. Handshake allows the server and the client to authenticate each other, to negotiate encryption and MAC algorithms, to negotiate the keys. And so there are several messages which are coming up in the next slide. There are several messages which establish the capabilities, 4 phases actually. First, we talk to each other and say, well, what is it that you can do, what is it that I can do, right? So a little iPhone or some other smartphone may say, well, I cannot do AES, I can only do 256-bit this and that, right? So that is done in the first phase. Then they do the authentication, server authentication and the key exchange. So server is authenticated first, that I'm talking to the right bank, that I'm talking to the right company, and then you get the key. And then the client is authenticated next, and the key is exchanged, and then finish. So here are the messages in 4 phases. This is phase 1, the first dotted line. Up to the first dotted line is phase 1. Then this is phase 2, this is phase 3, and this is phase 4. Alright, phase 1 is simple. Phase 1 is simply establish the capabilities. Is that client says, and notice that it all goes in clear, it says, look, I am so and so, and I can use these protocols, these ciphers. My version is so and so. So basically, it will say that I am going to use version 3.1 or 3.2, whatever version, and that I am going to use this encryption scheme, this compression scheme, and here is my random number. And the server then selects from these choices. So if the client says I can do only SSL version 2, then the server has to either select that version 2 or reject it. Right? If the client says I can do version 3.2, server can say, well, I can do only 3.1, so I will take 3.1. So the client specifies the highest it can do, and the server takes the highest that it can accept. So that response comes back. So it says, hello, here is the cryptographic algorithm I have selected, here is the compression algorithm I have selected, and here is my random number. All of this is done in clear. Now it is not very protected because somebody could change along the way, and this has been done. Because if suppose this guy says I can talk SSL version 3.2, somebody in the middle can change it to version 2. And then version 2 will be negotiated. And then that person will be able to break it. So that's why they have, actually there are 2 protections for this. It will come up in the end here. But there are 2 protections for this. First of all, this is SSL version 2 will not be allowed. And second is that they check out that even though these messages are not encrypted, they were not changed. That will come up in a minute. Alright, so once we have agreed on the encryption, then this is the optional part where server is authenticated. If server is authenticated, then the server sends its certificate, it sends a key, and it sends a certificate request. Actually, certificate request is misnomer. I find it confusing. When somebody says certificate request, it looks like I'm asking, please send me your certificate. That's not what it is. It is the CA. It is basically a message in which I tell you, which I send this, the CA's name, the certificate, his certificate, and here is the who the certificate is from. Kind of confusing, but anyway. So that is all certificate, and then finished. Hello, done. So these messages are sent one way. Now, once you have this whatever has been done from here, the client sends a certificate, and based upon the random numbers, it generates what we call PMS, pre-master secret. So that is the first step in generating the master secret, and master secret is the master key. But before we generate that, we generate PMS, and that one is encrypted with the server's public key. That makes sense, right? We know the server's public key, and we send the PMS there. Based upon that PMS, both sides can compute the same master key. So both sides can compute the master key. So this one has computed, this one has computed. The master key is not exchanged, but they have computed it, right? And then this says certificate verify. Basically, that it's all done. The end of this page. Then there is a change cipher spec. So this is actually phase 4. And this is the message which actually belongs to the other protocol. This is one byte message, says that now let us use that key to communicate. And then this side will send hash and MAC of all previous messages. So this will send hash and MAC. So it will combine all of these messages and hash them and get the message authentication code and send it. So if any of these messages were changed by anybody, now this is encrypted here, right? This will be detected here, and this one will do the same thing. It will say, okay, let's go with the new key, and here is my hash. So this one will also send hash and MAC of all the previous messages onto this side. So this can verify that the other side also got the same messages. All right. So that's the trick, is that you can communicate in public openly without encryption. However, you can still protect that by having this kind of MAC later on, message authentication code later on. Right. That is one thing. And the second, basically, let's see. And everything else is standard actually. So most of the other protocols that even SSH and other things, they do exactly the same thing. They negotiate first. Once they have negotiated, then they generate the key, and and I don't know whether SSH is after SSL, but now the later ones will do this as well. All right. So all the messages for the handshake are TLV included, TLV encoded, and all of you know what is TLV: type, length, and value. So there might be 1 byte of type, 1 byte of length, and then whatever is the length, that many value fields, right? So types are, these are the messages 1, 2, 14, 12, 16, 13, and so this basically covers all of these messages here, plus some that we didn't probably show. So that includes client hello, server hello done, client exchange, server key exchange, certificate request, certificate. See, the thing is, certificate request means CA name. All right. I think this probably means that these are the CA names I understand. So when you supply the certificate, supply me from one of these people. I think that would be a big list, though. I don't know. And then certificate sent by the server, and certificate verify the signature of the hash of the messages, and handshake finished is okay. So that's another point here. What they do is for taking the hash, they divide the messages into 2 halves. Actually, let's say they divide into 32 bits and 32 bits, first into blocks, and then they divide each block into 2 halves. The left half is done by MD5, and the right half they do by SHA-1, and then they exclude both of them, and then they send it over. I think previously they were not exclusion-ing, they were just going to send both of them, and then they realized that that is weaker. So really the stronger thing is to combine both of them into one and then send. So that way it turns out that if you break only one algorithm, suppose you break MD5, right, your messages are still protected because the SHA will not match. All right, if you break SHA, the MD5 will not match. So they thought by using 2 algorithms, they are getting the strength of 2. But if you keep them separate, then you're really not getting the strength because half will be broken and this half will not be detected by SHA. So then they have to now exclusive OR. So if either half is broken, then the whole thing doesn't work. Little bit more detail about the first phase, the capability negotiation. So these are the methods which are supported. These are the encryptions which are supported. So for the key exchange, now remember the key exchange method was Diffie-Hellman. We talked about Diffie-Hellman. is that you send some numbers to me and I send power of those numbers back, and then we can figure out what the common secret is. So that is the method which is generally used. You could also use RSA. Now Diffie-Hellman has three methods. Three different variations of Diffie-Hellman they use. First is called fixed Diffie-Hellman, second is called ephemeral Diffie-Hellman, and third is called anonymous Diffie-Hellman. So fixed one is the standard one that we have talked about, where you use the public keys and send the generator and your random number and so on and so forth. And so that is the standard one. But ephemeral means temporary. One-time secret key is generated after the certificate exchange and authentication. So this one basically does not use the fixed public keys. So after you do the certificate exchange and authentication, then you generate a secret key, and that is used just one time. So this is why it is called one-time Diffie-Hellman, or temporary Diffie-Hellman, or ephemeral Diffie-Hellman. Then the third one is anonymous Diffie-Hellman. In this case, there is no authentication done, only public key exchange done. Since there is no authentication, this is subject to man-in-the-middle attack. Right? MITM, man-in-the-middle attack. And because there is no authentication, anybody else can play in between. But there are some certain circumstances where you don't need the authentication, or or you cannot do the authentication, so you just use that. So obviously this is the weakest, this is the second, and this is the strongest one among these three. And then there is Forteza, which is basically using hardware, using PC cards. So if you want to negotiate with your PC cards, then that is the name of it. So that is the key exchange method. Cipher, the encryption methods which are supported are RC4, RC2, DES3, DES40, IDEA, and Forteza. By the way, DES40 means 40-bit keys, and DES uses 56-bit keys. Right? So why 40-bit keys? Well, there was a period when the United States prevented any company from selling any encryption cryptography equipment to any other country if it was stronger than 40-bit. So during that period, inside the country, we will all use 56-bit or 112 bits or whatever encryption, but if it goes across the US boundary, it has to be 40-bit. And I remember in those days, every company discovered a way to get around it. Every US company had a branch in Ireland or some other place, and they can sell it, but US cannot sell it. Finally, US realized that this is not very effective, so nowadays they don't enforce that law. I don't know whether the law has been removed or is still on books, but now people can exchange. And in fact, in between there was a period when people complained, the banks complained, they said, look, we cannot do financial transactions with 40-bit keys. There is a lot of danger. So they said, okay, all right, we will give an exception for financial transactions. So there was a period when 40-bit, and then there was a period for exception, and now there is a period where there is no rule, basically. So that's why many of these things have 40 bits in between, so that's 40. All right, MAC algorithm. So MAC is MD5 or SHA, Cipher, stream or block, is exportable, true or false. So these are all the fields that you have to fill in along with. So you select one of these and then you specify. So the thing is that if you specify RC4, clearly it is a stream. Clearly, now the question is whether it is exportable or not, maybe true or false, depending upon the size of the key. Right? Here exportable has to do with the United States. And the hash size, key material used to generate the key, and then the IV size of the IVs for CBC. So all of these fields are there in those messages, and if you want to know more about these are the URLs from Wikipedia. So master secret creation. We first, a 40-byte value based upon the nonces is created, 48 bytes, which is long, 48 times 8 bit, 384 bits. So that is the master secret. And how it is generated? It is generated using first a pre-master secret, which is exchanged using either RSA or Diffie-Hellman, and then you hash it. How you hash it? You take the MD5 of the pre-master and you take the SHA of the letter A. All right, and then you do the pre-master secret again, and then you take the random number selected by the client, and then you take the random number selected by the server, and there are a few more fields. Actually, it is given in the book. It's a little bit longer. You take all of that and you do MD5. That gives you a master secret. And there are a few more letters actually like this. Why letter A, I have no idea, but basically they have letter A, and then the next one is letter BB, and then letter CC. So they just generate some random numbers, random looking numbers, because SHA of A is probably not, I mean, once you compute it is not random. So you calculate all that and you get the master secret from pre-master secret. And then the cryptographic parameters are client write MAC secret. So this is one parameter. Its name is client write MAC secret. So this is the key that the client will use to encrypt. Oh, sorry, client write MAC. This is the key that the client will use to compute MAC. Client's MAC key. Then a server write MAC secret. That is the server's MAC key. A client write key. So that is the client's encryption key. Server write key. Server's encryption key. Client write IV, which is initialization vector, and a server write initialization vector. And all of these, or many of these, are generated by hashing the master secret. So master secret is generated by hashing the pre-master secret, and then by hashing this, and there is the whole formula for that. You can get all of these different secrets, different keys. So all of these keys are generated from the master key. All right, so that finishes the first protocol among the four that we talked about. Again, going back, SSL has four protocols. The first part is the handshake protocol. So we talked about that so far as to what the messages fields are, what are the different cipher specs, etc. allowed. Now we go to the next one, which is the change cipher, which is actually pretty simple compared to what we have gone through in this one. It's just one byte message which has a particular byte pattern which says here, let's start those values that we computed. Change cipher spec protocol. It's a single one byte message and causes negotiated parameters to become current and something. I think this could have been just part of the handshake. The reason they did not make it part of the handshake is because handshake is done once, change spec is done many, many times. So after every few minutes we might change the specs, and so we might negotiate a new key, so we don't do the complete new handshake. Because we already have a master secret, we just have to generate the keys. So that's why they kept it separate protocol, gave it a separate protocol. But this is basically saying that let's use this secret, let's use the keys that we just computed. Alert protocol is again simple. Basically, it has 2 bytes. First byte says what is the level, and the second, what is the level? The level could be either warning or fatal. Fatal means stop right away, immediate termination. Warning is be careful, but we continue. So that is 2 levels of level. And then the alert. Alert could be one of these numbers. 0 means close, 10 means unexpected message, 20 means bad record, and so on and so forth. And the list continues. Each of these type is either fatal or warning, and either SSL or TLS or both. So this one was used only in SSL version 3, this one is used only in TLS, and so on. So TLS in particular has much longer list of alerts than SSL version 3. Certificate revoked, certificate expired, unsupported certificate. So you get this kind of message, and then it could be warning or fatal depending upon what the user wants to do. So generally you see these warnings flashed on your screen, and the user generally says continue, or could say stop. Finally, the record protocol, which is the bottom of the all four protocols, as we saw here, the record protocol. This is the encryption and decryption. So this is also straightforward. Basically, you use whatever algorithm you selected, and the main thing to know is that the message is compressed before encryption. In HTTP, there is a lot of redundancy, right? And therefore, message is compressed. And before encryption, that reduces the number of bits. And then the integrity is done with whatever the selected HMAC, similar to HMAC but different padding. So that is what is described next. Basically, you take the application data, break it into blocks, each block is compressed. And then the MAC is added to each block, and then it is encrypted, and then we add the headers and we send it off. Alright? So notice that the MAC is encrypted inside this. This is basically MAC then encrypt. And so the only new thing here is the compress. All exchanges are in record. Now this is for the record protocol. The records can be as long as 2 raised to 14 or 2 raised to 16 minus 1 bytes. Standard allows multiple messages in one record or multiple records. So you could put, it's basically what it says is that this is many-to-many relationship. You could have many messages in one record or one message in many records. Most implementations use one message per record. So although this is allowed, implementation just take every message that comes from HTTP or from SSL for that matter and put that into one record. There are 4 record types: change, cipher, spec, alert, handshake, and application data. So basically the record protocol looks like this. You have a record type followed by version number followed by the record length. That is just the header, and inside this there will be messages. Each message will have a message type, message length, and the message. So each record can have many messages or could have part of a message. So the record could belong to one of these protocols. It could belong to the change cipher protocol, could belong to alert protocol. If it belongs to change cipher protocol, then it is just 1 byte, 20, and that's it. There is no version number, there is no record length. If it is alert, then it will have the record type of 21 and then 2 bytes. There is handshake, then we talked about that earlier, and so on and so forth. So that finishes SSL. And let's just summarize one more time, and this is the key, that SSL runs on the top of TCP, now not UDP, TCP. It has 4 pieces of protocol, sub-protocols: handshake, cipher change, alert, and the encryption protocol. And everything from these 4 goes through that protocol, and therefore it is encrypted. Except, obviously some of the handshake messages will go through clear.